Today, we're digging into a truly ambitious project. It's a blueprint for a new kind of mathematical language, one designed from the ground up to be understood perfectly by both humans and machines.
So, let's just get right to the heart of it. Mathematics, believe it or not, has a secret language problem. And it's not that the language is hidden, it's that it's split right down the middle. You've got this powerful, intuitive dialect that mathematicians use to dream up incredible new ideas, but that's not the same language computers need, not even close. Computers need something rigid. And that gap, that's where the mistakes, the bugs, and a whole lot of frustration come from.
And you can see that conflict right here. On the one hand, you have human math. It's amazing. It's driven by gut feelings and big creative leaps. But it's also kind of informal, and that means it can be ambiguous. On the other side, you've got machine math. It is absolutely, ruthlessly rigid and verifiable. And its greatest strength, that it demands perfect precision, is also its biggest weakness. It just can't handle the fuzzy logic that we humans navigate without even thinking about it.
So, what do? How do you possibly build a bridge over that gap? Well, the document we're diving into today proposes a really bold solution. Create a completely formal language for logic itself. A way to take those brilliant, sometimes messy human insights and translate them into the cold, hard certainty that a machine can check. 100%.
And look, the ambition here is just massive. We are not talking about just another programming language. Nope. This is a blueprint for the one thing we're missing, a single language of perfect precision. A language that is crystal clear to a person reading it and provably, mathematically correct to a computer. Something designed to express any mathematical idea you can think of.
So, to pull something like that off, every single idea in this language, every concept, has to be built on this rock-solid three-part foundation. You can almost think of it like the DNA for an idea. What does it look like? Does it actually follow the rules? And what does it really mean?
The first pillar is syntax. This is just the grammar. It lays out the symbols we're allowed to use and how we can put them together. So this rule you see here, this is basically how we teach the language a new word. That little double slash thing just means is defined as. So we're saying, hey computer, this new word, this identifier, is now defined as this expression over here. It's the absolute bedrock, the grammatical rules of our new language.
Okay, second pillar, typing. See, just because you can write something down doesn't mean it makes any sense. The typing rules are the laws of logic. A rule like this one is super important. It says, if you can prove everything in the list of premises, that's the stuff above the line, then and only then are you allowed to make the conclusion, the judgment, that's sitting below the line. This is the system's guardrail. It's how it makes sure every single step is logically sound.
And that brings us to the third and maybe the most profound pillar. Meaning, or, semantics. It's not enough for a statement to be grammatically correct and logically sound. It has to actually do something. It has to mean something. This is where the whole category logic idea comes to life. A rule like this one connects our abstract symbols to real, living mathematical objects. You can think of those double brackets as magic quotes. They're asking, what is the deep, universal mathematical meaning of this symbol? This makes sure we're not just playing with empty symbols, we're doing real math.
So, okay, we've got this super precise, powerful language. But this whole approach, this categorical way of thinking, it comes with a superpower that makes it unbelievably efficient. It's a principle called duality. And honestly, it's like getting two theorems for the price of one. To get it, let's start with an idea we all know. A product. You see the little X symbol there? It's just bundling two things together. Think of coordinates on a map like XY. You need both. Proving things about how products work is a pretty standard task in math.
But what if proving one thing, let's say a theorem about how these products behave,
What if that automatically gave you the proof for its exact opposite for free? So the proof for something called a coproduct, which isn't about bundling things, but about choosing one thing or the other.
Now, this isn't just some cool philosophical idea. It is a mechanical rule that is baked right into the language itself. Look at this infer dual theorem command. It literally takes a theorem that you've already proven, in this case about initial objects, which are kind of like the ultimate starting point in a system. Then, just by flipping all the arrows in the logic, it automatically spits out a brand new, totally valid proof for the dual theorem about terminal objects, the ultimate endpoints. It's a genuine 2-for-1 deal on mathematical proof. It's incredible. The real power of a language like this, though, it becomes clear when you see the sheer scale of the ideas it can define. We are talking about the grand, unifying structures of modern mathematics. I mean, the really big stuff. Let's just take a quick tour, a glimpse from the summit. First up, adjunctions. Okay, I know that formula looks intense, but the idea behind it is absolutely breathtaking. Think of it like a mathematical Rosetta Stone. It reveals when two totally different mathematical universes, say the world of geometry and the world of algebra, are secretly speaking the same language. It gives you a perfect dictionary for translating ideas back and forth. Being able to formally define a connection this deep, that's a huge deal.
Next, we can define monads. Now, if you've ever written a line of code, you know that programs have to deal with the messy real world. Things like user input or writing to a file or handling an error. A monad is a formal mathematical structure for taming all that complexity. It's a blueprint for sequencing operations and handling these side effects in a clean, totally predictable way. And with this language, a monad stops being just a clever programming hack. It becomes a fundamental mathematical object that we can build and reason about with absolute certainty.
And the power just keeps building. With this, we can define a Lawvere theory. The best way to think about this is as a master blueprint for an entire class of things. For example, a monoid. That's just a simple structure like addition where you can combine things. Well, instead of defining just one monoid, this T-mon you see here captures the entire theory of all possible monoids. It's like having the architectural plans for every single building of a certain type all at once.
And then, at the very summit of this mountain of abstraction, you find things called Grothendieck Topoi, a topos. Whoa. The best way to think of it is as a completely self-contained mathematical universe. It's a place that has its own idea of what a set is, and it has its own internal logic. And here's the wild part. The logic inside one of these universes might be totally different from our everyday logic. Imagine a universe where a statement isn't just true or false. This language gives us the formal tools to actually build and explore these bizarre alternate realities.
So, after that absolutely dizzying tour of abstraction, it's a fair question to ask, why? Right? Why go to all this trouble? The answer pulls us right out of abstract theory and back down to some very, very real-world stakes.
And it really comes down to this, the hunt for 100% reliable software. By finally bridging that gap we talked about, by getting rid of the ambiguity between human thought and machine code, we can build our most critical systems on foundations that are not just tested, but formally proven to be correct. Can you imagine an aircraft control system or a global financial network where a computer has mathematically verified that the core logic has zero flaws? That's the dream. That's the goal.
And that really lays out the ultimate ambitions here. First, to automate the tedious, boring work of checking proofs so mathematicians can focus on being creative. Second, to build that perfectly reliable software we just talked about. Third, to use this formal structure to discover new mathematical universes, like those Topoi that we haven't even dreamed of yet. And finally, maybe most importantly, to gain a much deeper, more fundamental understanding of logic itself.
Which leaves us with a final, pretty mind-bending thought. If we can actually succeed in creating a language that perfectly captures the structure of logic, of algebra, of geometry, what's the next big idea we should teach our machines to understand?